Hello everyone and welcome back. Now in the previous two videos we talked a lot about introduction to mathematical modeling. This was through the ABCs and the five-step method, talked about unit analysis, the classes of models, how we should approach modeling. We even did a little example. So now what we're going to do is really get into the thick of it. And we're going to begin our first of 3 units that we will cover over the class over this semester. And this first unit is going to be on optimization models. Now, as the name indicates, optimization models, the goal is to optimize something. Now, optimize is just a mathematical term for either minimizing or maximizing something. And you do this all the time. Maybe if you gamble, you try to minimize your loss or maximize your profit. Try to maximize productivity, maximize the amount of money that you can get out of something, or minimize the amount of money you have to pay. There's always some sort of strategy going on where you are trying to optimize the output of a system. What we are going to do is we are going to quantify that mathematically. And as we walk through these units, we are going to do this in an example-driven manner. Now, the first thing that we will talk about is single variable optimization. Now, you might have actually done a little bit of this in your calculus class because we know that maximums and minimums, they're related to the derivative of a function. These are the critical points along a function. And so therefore, we know that we can find them, at least with a single variable calculus methods, of just setting the derivative equal to 0. So maybe some of this lecture is going to be a bit of a review for you, but in the second half, we're going to talk a little bit about sensitivity analysis. This is related to the robustness of the model. It tells us, if we have a little bit of uncertainty in building a model, is it okay that we're not 100% correct? Okay, so let's go ahead and get started. Again, I want to do this in an example-driven manner. Here's my example, okay? Now, here we have a pig. So pig weighs 200 kilograms. So weighing 200, actually let's do pounds. 200 pounds, gains 5 pounds per day. Okay, so we have a rate. And it costs 45 cents to keep. 45 cents per day to keep. Okay? The market price for pigs is 65 cents per pound. So we have a lot of rates in here. But falls 1 cent per day. Okay, here's my question. When should we sell the pig? To maximize profits. Okay, so there it is. There's the key word when it comes to optimization. We're asked to maximize something. So that means that we've got an optimization problem. And in particular, we want to know, when should we actually sell the pig, right? So it's a question about time. This is a dynamic model. Well, just like we did with the ski goggles, we're going to start by listing off the variables. So let's do this. Let's say let W equal to the weight of the pig. Okay, so that's clearly something that we care about. T, this is the number of days until we sell the pig. Sell the pig. Okay, let C equal to the cost of keeping the pig. Okay. And we're going to do variables for everything. We're going to say let little p equal to the market price for the pig. So you can probably start to connect these things to the original word problem as we're writing them out. Let's say let R, let's let this be the revenue obtained from selling pig. And finally, the thing that we really care about, P, is the profit. All right, so that's revenue minus expenses. Now, we have a lot of information that we're going to try and put all together here. So how can we do this? Well, first of all, the weight of the pig, W, as a function of T. Let's take a look at this. The pig is initially 200 pounds, and then every day it adds 5 pounds. So my equation, 200 plus 5t. Now, the first thing you should do is you should take a look at the units. The weight is in pounds, 200 is in pounds, 5 is in pounds per day, t is in days. You multiply those two things together, you get pounds. Okay, so units are good. Similarly, little p, the market price for the pig. This is 65 cents. Pig is, 65 cents per pound. But it loses 1 cent per day. Okay, so this is P, which is in dollars per pound, okay? So let's take a look at this. 0.65, that's 65 cents per pound. That's dollars per pound. Same thing over here, 0.01t, that's in dollars per pound. Okay, the cost of keeping the pig, well, it costs us 45 cents per day. Of course, we're going to do this in dollars because we've already started with dollars here. So that is 0.45t. Again, analyze the units. Be very, very careful. Be skeptical even. And then the revenue, this is going to be, well, it's going to be the profit from selling the pig times the weight of the pig. So this is P of t times W of t. All right, so this is the profit per pound. This is the number of pounds. So this is just profit here. And then, the revenue. And then the profit, this is going to be the revenue minus the cost. Revenue minus expenses. So put it all together. We're going to get one nice equation that we want to analyze here. Here's our equation. So therefore, we built our mathematical model. It is a profit as a function of time. This is going to be PW minus 0.45t. P and W are right here. We're going to wrap all of this up, and this is going to give me 0.65 minus 0.01t, that's little p of t, times the weight, that's 200 plus 5t, and then minus the cost, which is minus 0.45t. It looks ugly, but that's really just a quadratic equation, right? And the goal here, so let's actually, maybe we should write this out. The goal, maximize P over t greater than or equal to 0. That's what we want to do. That is our goal. We've got a single equation for the profit, right? We put everything together. We have all of these variables that came out of just this sentence here. We put them all into equations. We've boiled it all down to a single equation of a single independent variable t. Now what we would like to do is maximize this thing. Well, again, we said that maxima and minima of a function, those are critical points. Critical points come from setting the derivative equal to 0. So what we're going to do is we're going to take the derivative of p. So I'm going to go ahead and compute this for you. The derivative of p is actually 8 minus t over 10. Very, very pretty derivative. Ugly looking function. Multiply it out, it's not that bad. So clearly, p prime of t is equal to 0 if and only if t is equal to 8. So now the question is this a maximum or a minimum? So maybe I'll just even write it. So hopefully if you took a calculus class before this, you know how to answer this question. There are multiple different ways. You can use the first derivative test, or you can use the second derivative test. Now, the second derivative test is really, really easy here, right? Because the second derivative is just equal to minus 1 over 10, which is less than 0, which implies that the second derivative at the critical point is less than 0, which implies that we have a max. So we have a maximum of our function. We actually identified one using, this sort of old school calculus processes. In fact, this is just a simple little quadratic curve. So in some sense, it just kind of looks like this. All right, so if this is just what my curve looks like, here is my maximum at 8. So clearly, I have an answer. I should sell the pig after 8 days. Sell the pig after 8 days. Perfect, right? Nice little simple word problem wrapped up in a nice little bow for you using just basic calculus methods. What was the hardest part of all of this? The hardest part was taking that sentence and turning it into a mathematical model. Once it's a mathematical model, hopefully, it's just a plug and chug kind of thing. We can get it done. But we can ask ourselves, what if we have a little bit of uncertainty in our model? So that is, what if we don't know exactly what the rate of the price for the pig is? So in this case, for example, we said that the rate is falling by 1 cent per day. What if the price is a little bit variable? We actually didn't know that the pig would cost 1 less cent per pound per day. Well, we can actually ask ourselves, if we sort of say R is equal to the rate falling per, or market price falling per day. Okay, so what does it actually fall at? So we had R is equal to 0.01. It gave us this piece of this equation right here. So what if that's a little bit off? Okay, well, let me give you a little table. So here is what I have. I'm going to give you the value of R. So if I'm going to change it in here, I'm going to go through all the computations for you. I'm going to tell you when you should sell the pig. Okay, so if it falls by 0.008 cents per day, so less than a cent per day, right? 0.8 of a cent every day, you should sell it in 15 days. So what does that tell you? Well, you're not really losing that much money day to day. So you should hang on to the pig, let him get nice and fat. Okay, so then, if it's 9/10 of a cent, well, okay, so you're losing a little bit more money each day, then you should get rid of them sooner, right? It's costing you money to keep them. So around 11.1 days. Okay, well, we just did 0.01. In the previous example, we know the answer is 8 days. All right, so what we're seeing is a general trend. The more it costs, or the more money you lose per day, well, the sooner you should be selling this pig because it's costing you a lot of money. Now let's look at another one. What if it is 1.1 cents that you lose each day? Well, here's a pretty big drop. 5.5 days, right? So get rid of the pig as soon as possible because you're losing a lot of money on this thing every day. Okay, so, that's great, right? But the problem is getting all of these answers required me to resolve the problem the whole way. I don't want to have to do that, right? That's a lot of work. So the way that we can actually quantify this is using what's called sensitivity analysis. What we want to do is we want to know how sensitive our result is with respect to maybe some unknown parameter. So for example, if I don't know what this rate is, how sensitive is my number of days to sell? How sensitive is my profit, right? Am I losing a lot of money if I'm selling at 9/10 of a cent instead of 1 cent? Right? These are the questions that you want to ask yourself because again, if this is a mathematical model, we don't have complete information. We want to ask ourselves, is this thing robust, right? If I change a few of the parameters a little bit, are things going to stay relatively similar? So, well, how do you do this? Okay, well, what I'm going to use is a parameter R, and that parameter enters into my profit equation right there. So that means that I've got a new profit. Well, I've got the same profit equation, but I'm going to use a variable or a parameter in here now. So this is going to be minus RT instead of 0.01T, 200 minus 5T, and then minus 0.45T. Okay, so the only thing that changed is I put in a parameter here. If you put R is equal to 0.01, you're going to repeat all of the analysis that we just did. Now what I can do is I can ask myself, what is the time to sell for a general value of R? Well, I just repeat this, right? Again, I want to maximize the profit. That means I want to take a derivative, and I want to solve when the derivative is equal to 0. So here you go. I'll give you the derivative. So minus 2, and then it's a little uglier. That's because we have a parameter in here now. That's okay. We can handle this. And minus 7, all divided by 5. You set that thing equal to 0. Well, you can back solve for t. This gives you, as a function of r, 7 minus 500r divided by 25r. So what that formula is that is a general formula. So no matter what the price is falling by per day, I can always tell you when you should sell that pig, right? That is how I could fill in this chart right here. In fact, that's how I did it. I just didn't tell you. So, for example, when r is equal to 0.008, then t is going to be 15. If r is equal to 0.009, t is going to be around 11.1. Okay, so what this tells us is when we should actually solve or sell this thing based on that rate. Okay, let's repeat the same thing, but let's imagine the growth rate of the pig is variable. So for example, let's let g equal to the growth rate of the pig. And remember, before we had 5 pounds per day. Now, that means that the weight of the pig is equal to 200 plus GT. Okay? And when you put this back into the profit equation, I'm going to revert the R variable back to its original 0.01, so we don't have multiple parameters in here. Let's do 0.65 minus 0.01 t, and then the weight, 200 plus gt, and then minus 0.45 t. Okay, so now let's do the same thing, right? Essentially, I've got back to exactly the same thing I just did with R. So I want to maximize the profit. I want to know, regardless of what the growth rate is, when should I sell? I want a nice little formula that tells me exactly when I should sell. Well, P prime of t is equal to, so I'll do the computation for you. This is going to give you 2gt, and then plus 5, and then 49. There's a lot of annoying little variables here. I'm trying to keep things in whole numbers for you. It's entirely up to you how you want to present these numbers. But the point is that you can solve the derivative of this thing equal to 0, and you can get the time to sell as a function of this growth rate. So you got 13g, and then minus 49 over 2g. So what that tells me is that if I know what the growth rate is, I throw it into that formula that says sell the pig now, right? That's exactly what this is covering. Now, this is going to tell us, when we should sell. This is exact, but we might have a question of, what is the relative change that's taking place here, right? So things about, percentage change. So sometimes you'll hear in the news when people talk about stocks say it was a 10% drop, right? So 10% of $1 is only 10 cents, but 10% of $1 million is $100,000, right? So all these things are sort of relative, right? You want to know how much relative change is going to happen. This is an absolute change. It's giving you exactly what's changing. This is good, but this can't be done all of the time. So the question is, how can we actually find a relative change here? Well, let's go back to my R variable, for example. Well, in that case, I could say the change in when to sell divided by when you sell. So this is a relative change in when you sell divided by the relative change in the rate divided by the current rate. So what I have is relative change divided by relative change. These deltas, these little triangles, that just represents change, okay? So change in when you sell divided by when you actually do sell over the change in the rate divided by the current rate. Well, of course, this is calculus, right? So we want to do this instantaneously. So if we let the changes go to 0, this is going to converge to the derivative of R with respect to t times, the derivative of t with respect to R, pardon me, did that upside down. T with respect to R times R over t. That comes from the fact that these relative changes, these are secant lines, as you are getting those two secant points closer and closer and closer together, you are converging into a derivative, right? This is exactly what the definition of a derivative is. It's the instantaneous rate of change. This right here is called the sensitivity. This is the sensitivity of t with respect to R. This is how sensitive when you should sell is relative to that parameter R. So if R changes just a little bit, are you going to get a massive variation in when you should sell? Or is it going to be a relatively small variation in when you should sell? Right? And the way that you're doing this is doing everything relative, right? So for example, I was told that I should sell after 8 days when R is equal to 0.01. Okay? So what you're doing is a 1 day swing on that thing is going to be relatively large, right? That is 1/8 or 1/8 of a swing from an 8 day period. That's an even bigger swing if I was told that I should sell in only 2 days, right? Because that's telling me I either sell it a day before or sell it a day after. 1 in 3, right? Relative, that is a huge percentage. So that's what sensitivity is telling you. It's giving you the relative change, right? So for example, if I told you to sell a pig after 100 days, then I said, just wait 1 more day. You say, whatever, 1 more day. I haven't been waiting. I've waited 100. I might as well just wait 1 more, right? It's not a big deal. But if you only waited 8 days and I told you to wait 1 more day, you say, oh, that's a lot of days, right? Relatively, that's a lot. I've already waited 8. You told me that I only had to wait 8, right? So there's sort of this like almost like kindergarten logic that goes into it, right? It's like, well, you told me it was only going to be 8, so why isn't it exactly 8? Now, question is, now we've got a formula. Let's do it. Let's actually do this. So dt dr. Again, I had a formula written on the bottom of the board before it was cleared here. You can take the derivative of that thing with respect to r. This is going to give you minus 7 over 25 r squared. And this tells me that the sensitivity, S, of the time to sell with respect to r is equal to minus 7 over 25 RT. That's just multiplying the R over T into this formula. Okay, so let's take a look. My sensitivity, if I was told to sell after 8 days when my rate was 1 cent lost per day, this gives me minus 7 over 2. Now, how do you actually read that? Okay, this says R goes up by 2%, then T goes down by 7%. So they're pretty close to each other, right? They aren't that sensitive. Because if the rate goes up by 2%, that means that the number of days we need to wait goes down by like 7%. It's not that much of a change relative. And in fact, you can actually do the same thing for this parameter g as well. So you could do s of t comma g. Remember, this is the derivative of t with respect to g. So this derivative right here times g over t, which this case is going to be 245 over 2gt. Okay, so just computing a derivative. These are easy things to compute. You can do this very, very easily. And in particular, again, if you're going to do g is equal to 5, again, from the beginning of the lecture, we were told that we need to sell after 8 days. So s of 8 comma 5, this is going to be 3.0625. So how does this actually read? Well, okay, this is about 3, okay? So this tells us a 1% change in G, and then that is going to cause about a 3% change in T. That is what that is telling you, right? So this is really sort of like almost like a business analytics. This is how you sort of properly talk about these things in the real world. These are relative change rates. These are sensitivities. So very small change. A 1% change in G causes about a 3% change in T, right? It's not a crazy relationship between these things. Well, we can do the same thing for the profit as well, right? So let's do the profit in terms of G. So here's my profit function, right? And I can put my T value, or sorry, my T function right here into this, so I get a function of G. So put T equal to 513 G minus 49 over 2G into P of T. Okay, this is going to give you something kind of ugly. It's going to take a little bit of work to clean it up, but I will give it to you right now, okay? So I cleaned it all up for you. You can just throw this into maybe Wolfram or Maple or whatever it is you like to do to simplify these, or maybe you can just have a little bit of fun doing it yourself. That's perfectly okay. But this is what your equation now looks like. 375, and then plus 10.5625 G. Okay, so what this is I figured out the optimal time to sell based on my parameter G. Then I asked myself, what is the profit that I would make? Well, I took that time to sell and I put it into my profit function. The result is my profit when I sell at the optimal time to sell as a function of that growth rate G, okay? But now I've got something I can take derivatives of, right? So then I can take a derivative with respect to G, and I can look at the sensitivity here as well. So in this case, I get, so this is going to be minus 150.0625 over G squared plus 10.5625. And so what you can do is you can compute some sensitivities here. So the sensitivity of the profit with respect to the growth rate, this is equal to, so essentially you're just taking this thing and multiplying it by G over P. So this is going to give you negative 150.0625 over G times P, and then plus 10.5625 G over P. Okay, so it's an ugly little formula, but it's just a formula. Do not get intimidated by that. And now I can actually plug in. So when my growth rate was 5 pounds per day, in fact, my profit, so I could just put it into this formula, my profit was $133.20. Okay, so that's how much the pig got me. And the way I got that profit is P of 5. I just put 5 into this equation. Calculator problem. So the sensitivity of the price with respect to, the profit with respect to the growth rate, when the growth rate is equal to 5, this thing is equal to 0.17, which, this is just 17 over 100. So what this really means for us, this can say a lot of different things. So this says pig grows 10% faster than expected. Okay, so maybe you're watching your pig and going, oh my God, look at this thing. It's growing at 10% faster than I predicted it would, right? I predicted it was going to grow at 5 pounds per day. It's actually growing like 5.5 pounds per day, right? That's my 10% faster here. Then the net profit on this thing is only going to be about 1.7% larger. So net profit is 1.7% larger. That's not that much, right? That's not that much. 1.7% of 133, it's like what, $2? Maybe a little bit more. So, okay, so what does that tell you about the model, right? This tells you something very, very important about your model. It's okay to be off, right? Because you're not really losing out on that much here. So, let's think about this. Let's zoom out and really think about what all of this says. I estimated my pig's going to grow 5 pounds per day. Okay. Now, turns out my pig grows, about 10% more than that per day. So maybe 5.5 pounds per day. Okay, that's okay. But I still predicted this. I got somebody coming to buy the pig on day 8. That was the plan, right? I predicted it. I said my growth rate should be 5 pounds per day. This is what all my other pigs do. And therefore, I should sell on day 8. This is the model that I built. So I go ahead and sell the pig on day 8. But what I realize is, shoot, the pig grew faster than I thought it would. So maybe I lost out on a little bit of profit. What this sensitivity is actually telling you is that you didn't lose out on much profit. The profit is only 1.7, or it only would have been 1.7% larger, right? You missed out on maybe $2. That is robustness, right? That's what we're seeing in these models. That tells us that we have, we can be off a little bit. Things don't change that much, right? We're seeing things like 3% changes or 1.7% changes or 7% changes. These are tiny, tiny, tiny little changes relative to the numbers that we're talking about, right? A 7% change in 8, that's like, that's hardly anything. That's less than 1, right? So this is saying that we don't really need to change the number of days that we sell for. Same thing up here. We don't really need to change the number of days that we sell for. So this is an important quality of our models. This gives us robustness. It tells us that it's okay to be off by a little bit. Pig grows 5.5, or the price goes down by $0.09 per day. That's fine. We can still use the original model. We can still do very, very well. That's what we are trying to look at when we talk about sensitivity. These percentage rates, these relative rates of change when it comes to these models. Okay, in the next video, we'll talk a little bit about Newton's method and how we can solve these optimization problems whenever we can't just do it with pencil and paper. So a little bit of computational methods in order to sort of enhance us or help us out a little bit. I'll see you in the next lecture.